So let's start. A warm welcome to Bioprocess Engineering. Today we talk about mass transfer. I'm so happy to have a couple of you here. So what we will do today is we will talk about mass transfer, but before we start with respect to mass transfer, we go back to the exercises we had at the end of the energy balance section. This was the exercise on citric acid production. Give me a second, so I will look out for this exercise. Yeah, this is it.
Professor, can you hear me?
Yeah, I can hear you. Go on.
So my question was about when we have to calculate the mass times the delta H, because I always got that value wrong, but then in the end I got the Q value correct.
Okay.
So it's a bit weird.
Okay, so maybe what we do is we just have a look in this exercise, and then you might tell me at what step the problem was, okay?
Okay.
Okay, so, oops, here we are. So, as a reminder, that was the exercise. So, it was citric acid is manufactured using submerged culture of Aspergillus niger in a batch reactor operated at 30 degrees over a period of 2 days. 2,500 kilograms glucose, oxygen, and so on are consumed to produce this and that. Ammonium is used as a nitrogen source. So the most important thing you realize at this exercise is what? So the number one thing you look at. So of course it's you ask about energy and so on. So you need to set up an energy balance and you need to calculate an energy balance. And as we said, if there is a reaction, we have the simplified equation where we then use an energy balance where we incorporate the heat of reaction. Yeah? And now the question is how to calculate the heat of reaction. And a very easy way to calculate the heat of reaction is everyone is invited.
The oxygen demand?
Exactly, the oxygen demand. So in other words, the first thing you look is
whether it's aerobic.
Whether the reaction is aerobic or not. Exactly. So if it's an anaerobic reaction, no way to calculate how much oxygen is being consumed because there will be no oxygen consumed. So that's very important. Don't forget that. That's the first look. If you have an energy balance to do, and if you have an aerobic reaction, you already lean back because your only job is at the beginning at least calculate how much oxygen has been consumed. And in this exercise here, the coolest thing all over is it's already done. So if you look at this exercise, you see, wow, they already gave me that 860 kilograms oxygen are consumed. So this makes you feel very good because this means that you don't need to calculate, you don't need to set up mass balances, you don't need to come up with an elemental balance, you don't need to come up with an electron balance in order to calculate how much oxygen has been consumed because it's already there. Yeah, in general, you would need to calculate that maybe first, but here it has been measured. So this is the real world scenario. You measure that, of course, and then you have your amount of oxygen. And then the only thing you need to do is you need to use this equation number in your formulary. As I told you, I do the same. I always carry my formulary with me. Night and day, wherever I am, I have my bioprocess engineering formulary with me. And then I go to energy balances, and in contrast to you, I have not marked the equation of the equations, and then I see that oxygen is minus the heat amount of oxygen consumed, and that's the 44 here. Here we are. delta Rxn for fully aerobic metabolism is minus 460 kilojoule per mole. So what you, by the way, what you have realized now is it took a while now for me to find this equation, because I never use my own formulary, because I have this minus 460 kilojoule per mole in my head. However, it's better to look it up in the formulary. So a wise idea is really be familiar with your formulary. Otherwise, things get complicated. Yeah. So in other words, I know how much oxygen is being consumed. I know it's aerobic. So I can simply set up the energy balance in this case. And I have a lot of sheets today because I have a lot of different lectures I want to do. And it's always the last one you look at. So here we are. So the energy balance you want to look at is, of course, the following. So here we are, citric acid. So it's, of course, I forgot the number, but you can also tell me the energy balance. Even better. Why should I look it up if you can tell it? Tell me the energy balance which is applicable here. So we have a heat of reaction, which contributes.
It's equation number 47.
47 sounds really good, although I don't know it by heart. But now you can tell me the 47 equation, and I will note it.
It's heat of reaction.
Yeah, so it's just give me the equation. Minus
Heat of reaction minus
delta
mass
H Rxn, yeah? Yeah.
minus mv
Minus
mv
M, yeah?
times delta H
Delta,
v
yeah?
minus q plus ws equals 0.
Equals 0, because we said we're in a steady state. And this, for my friends here, is what again, this term? Oh, this is of course not ideal here.
Latent heat of vaporization.
So the latent heat, the heat of vaporization, exactly. This is the heat required for cooling. So if it's positive, we need it for cooling, and this is what we expect. And this is the heat transported in with our stirrer. So then we just need to, what we need to do now is step by step calculate the heats. And if we look at the exercise, we see that, okay, citric acid is manufactured submerged culture. We have a heat input, which is the 15 kilowatt agitation, and we have water evaporated. So we need to bring in these two things. Okay, so let's start with calculating the heat of reaction. So we can directly go, because this is calculated based on oxygen. Yeah? Oxygen consumption. Okay, so we need to convert this 860, this is M. We want to calculate the NO2 is MO2 fold. So this is, we can directly put the mass, it makes life easier. It's 860 kilogram, yeah? And 60 kilograms. Fold. We convert to grams. Then we have kilograms. 1,000 grams are a kilogram. Fold. Molar mass of oxygen was... Oh. Molar mass of oxygen. 32 grams per mole, that's cool. So where do we need to put it? So we want to get rid of the gram. So therefore, here we have the mole divided by 32 grams. Now the grams get kicked out, kilograms get kicked out, and at the end we have...
Mole.
How much mole oxygen do we have at the end? By the way, I have not this calculation on my sheet, so therefore I rely on you because I have no pocket calculator with me. Are there first estimates for
26,875.
this is something we would like to put as 2 point something times 10 to the something.
2.7 times 10 to the power of 4.
Not round too much here. It's an interims calculation. So if it's 2.67, then say 2.67. So it's not that we want to lose precision. It's so say take care. If you use a scientific notation, I would always use with interims calculations. I would always go for 6 digits precision. Yeah. So then you would say 6 digits. If you have more digits, it's 2.67 something times 10 to the something. Also, if you use a scientific notation, yeah, that doesn't matter. Because that's sometimes a risk that people think if they put 260,313, they put everything. As soon as they switch to a scientific notation, they go to 2.6 times 10 to the. Not a good idea. Keep the precision. You just want to have it clearer that you know where you are. It's 10 to the 6 or something like that. So it's 2.67 times?
2.68 times 10 to the power of 4.
2.68 times 10 to the power of 4 mole. Okay, so there we are happy. And then we can, of course, calculate our minus delta Rxn is equal to minus 460 kilojoules per mole. Fold, this was this equation 44. Fold our 2.68 times 10 to the 4 mole. Bam, bam, and we end up with a couple of kilojoules. This should be the same as here. Here I have, what do I have here? Minus 1.24 times 10 to the 7 kilojoule. 10 to the 7, not 10 to the minus 7. Yeah, that sounds at least reasonable.
Excuse me. What was the value minus 460? What is that?
Equation 44.
Yeah, no, just the value minus 460.
Kilojoule per mole.
It's given.
Yeah, okay. 1 mole oxygen provides minus 460 kilojoule. Remember, because 4 electrons are transferred and 1 mole of electrons transferred are minus 115 kilojoule. Yeah, so that was where it came from. Okay, so this is our delta HRXN. The heat of vaporization, of course, you look up, you take the value from the steam table. I think the steam table was given in the Moodle exercise. I don't remember. So of course this value need to look up or it needs to be given. So then make sure that you take, of course, the heat of vaporization at the correct temperature. Otherwise you would use Zinsel-B heats to go up and down, but usually it's given at the correct temperature. Multiply that with the mass, don't forget that. And then you have your you have your latent heat, which goes in your equation as minus, of course. And then you need to calculate the stirrer power. But there is a question, and as you're not so way away, oops. That was...
Hey, thank you. So I was just wondering, for the Moodle homework, there were 2 tables, like one table given for the Moodle homework and one table in the Doran's book where the exercise relied on. And why are there for the same thing 2 different values? Isn't there like some value we can take for granted?
That's a very good question. And I can give you a very simple answer. The table of the Doran is the precise table, which is most likely based on measured values. My table is a table which is generated. So what I do is I use a polynomial approximation, and as all of you get different values, and then I approximate the values. So my values are less precise. However, for the exercise, if you calculate it, my values are the relevant ones, because my values are the ones where you will get then the precision. So of course, not the relevant ones?
Because we took your value, we did the exercise, but we didn't want to put your values, or the table.
Yeah.
Didn't get the right thing moved. We took the value from Prof, got it wrong.
Oh, that's strange. That shouldn't be. Then I put in my formula the wrong values. Then I use the formula then with the Moodle values. That's very good. This I have to correct. Yeah, yeah. Shouldn't be like this. Yeah. Then I didn't trust my own values. That was the problem. Yeah. No, but this is the reason, because my values are calculated. Yeah.
Okay, but there generally aren't two opinions like the one.
No. In general, if you have measured values, these are the values. And for these values, heat of vaporization, I don't think that there is in science a debate anymore. Yeah, this is with this, maybe with the 500 digits after the comma we start to discuss. But these are everyday values.
And in the exam, we're sticking to those of the Dorans again, or also with some arbitrary difference.
In the exam, it's simple. You're not allowed to carry the Doran with you, so therefore it's a good idea to use the value from the exam. If in the exam you say, I get this result with the Doran values, you get into trouble.
I mean, maybe you know the Doran values.
By heart. You've learned them by heart.
Students knowing Doran tabulated heat steam table values by heart make me nervous.
Why?
Okay.
Because you might use your brain cells for something which makes more sense. Of course, if you feel that this relaxes you, learning by heart steam tables, go.
I mean, if I have no use for it in the exam, I won't.
In Germany we have Wetten, das, haven't we? Is that still? Wetten, das? Gibt es noch? No more. But if there is a special edition, you might apply. I know the steam tables for water, and Thomas Gottschalk will be happy. Yeah.
I mean, you can go to an airport hut, I'm guessing and just get as a random fact at the beginning.
Okay, so that I have to check that, because this is interesting. It should be the real values are always my values in case of doubt.
It was in the MV delta HV calculation.
Ah, okay. So in the kilowatt is of course just something you need to convert to joule. Yeah, and you put then everything in this equation here. So we have now just calculated the heat of reaction. We have talked about how to calculate this, and of course with the stereo power you go in. Don't forget the power input is 50 kilowatts. So you need to take into account that this runs for 2 days. Yeah. So this is a power. A power is not an energy, just physics first class. Yeah, don't forget that. Energy is powerful time. So then you have to multiply that. So it's then, if it's 15 kilowatts, you need to multiply that by 48 hours, and then it's an energy, and this you need to convert then, of course, into kilojoule in order that you can subtract it. Okay. So that's about this exercise, and now my question to the internet: did hopefully this respond also your question you had in between? We vote for yes. Okay. Okay. So, then, if I find my mouse, we're done with energy balances, and we can go to the promised field of mass balances. Oh, yeah?
My question wasn't about this part, it was the next. So the HR times delta H. MV times delta H.
Yeah, but that's what we discussed. That's about the steam table. So you have your steam table. On the steam table, you have the heat of vaporization listed. You just take the delta, and we have discussed, obviously, that the value I have used was the wrong one. So you should have used the value of Duran, but this should be the other way around. So that was my error. Yeah.
So do we all get our points back?
Okay, thank you.
So I have to check that, of course. Yeah. In this case, you will get your points back. Maybe someone sends me a reminder email. Yeah, just that in order that I don't forget that. Yeah. Of course, then this was not your fault. Obviously, the problem was that the listed delta, the heat of vaporization listed was, I used another value for the calculation. And therefore, you had a problem to get the correct result. Okay?
Yes, understood.
And ash on my head, my fault, not your fault. Okay.
So in an anaerobic reaction, how should we calculate?
That's a good question. The question goes back to you. In an anaerobic reaction, how should we calculate that?
Heat capacity?
Yeah, the heat of vaporization, you mean, or what?
No, I mean the
Heat of reaction.
heat of combustion.
Yeah, exactly. You have to use the heat of combustion of all substances, and then you just use this formula where you subtract product sum minus educt sum, and then you get the heat of the reaction. The problem is, in this case, you need a complete mass balance. Yeah, you cannot start if you just know how much oxygen has been consumed. In this case, the mass balance, by the way, is complete. So you could have calculated that also based on the heat of combustion. However, this is, of course, way more complicated. It takes longer. So that's the point. If you can calculate something just based on the oxygen demand, do it. Things are easier and it's faster, because at the end, in this exercise, you convert it to mole, put it in the equation, that's it. Yeah? And then you have to do that, of course, for the heat of vaporization. And if your professor would not be so stupid to, in his formula, to use the wrong value, then everything would be fine. Yeah? Okay. Okay, so let's come to part 3, mass transfer. The promised part, mass transfer. You have already done the experiment today. So that's a cool day to start the lecture on mass transfer, because that's actually what you did in the lab course today, real bioreactor. How was it?
We'll have it tomorrow. We have it tomorrow.
Anyone did it today?
Yes. I did it last year.
Last year. So
I did it in our which homework?
no.
Can you repeat the question?
Everything is cool. No homework. Just the experiment with a mass transfer.
The KLA?
Yeah, Kelly today. That's mass transfer. Yeah, that's the oxygen. Cool.
Yeah.
That's cool. That's a bioreactor. Something is moving around, sparging. Vial next to it. A happy Vial, because he also likes this. And everyone is happy. Yeah? The only thing is not in our lab. We had to be in the technicum. But nevertheless, there's a lot of space. And the distillery is just next to you. This also makes you feel happy, hopefully. Okay, so, and now we will talk about what you did, more or less, in this experiment. So, yeah, mass transfer, this is what you should know. And before we start, we should think of where mass transfers in bioprocess appear. So today we have 4 hours, so we have 2 lectures in turn. And again, the cool thing is it's recorded, you can watch it again and so on. But nevertheless, I would like to proceed a bit. So today I try not to talk too long about topics which are not directly related to lectures, which usually works very good. Okay. So, there is not just one transfer process. So we have talked energy balances. We have talked about energy balances. And if we think of energy balances, we have talked of how much, so for example, in this cooling process for citric acid, we have said, whatever at the end, you need to remove, I don't remember, 2 times 10 to the 7 joule for this 2 days process. Yeah? So this is what we have calculated. So you know how much, you can calculate how much this costs, because energy is cost. If this is electrical energy, you can say, let's say if I have, if my kilowatt hour is to 40 cents, then I can calculate how much do I have to pay. Very simple. But is this, if you set up such a reactor, is this the only thing relevant with respect to cooling? If I ask like that, the answer is no. So what is also relevant? Of course, always the internet is also invited.
Yeah, or the shaft work that goes.
Yeah, okay, but it's just thinking of the cooler. So of course, energy input is the reaction and so on. But now, if we say we now want to set up the process, we want to calculate how expensive things are, and we look now just for the cooling. So we look for the energy which is required, but what is also relevant for such cooler?
Yeah.
The speed of energy transfer.
Yeah. In other words, the power. So the point is, if you have to remove whatever 10,000 kilowatts, and you have kilowatt hours, and you have 1 year time, then you can take a tiny little cooler. But if you have to do that within 1 hour, you will have to use a completely different device. And of course, the cost of such a device will be completely different. Yeah. So the cost of cooling not just depends on how much energy you have to remove, but it also depends on what energy you have to remove in what time. And this is energy transfer. Yeah. So of course this is relevant. So that's and this is relevant for energy. This is relevant for momentum transfer when we stir. But the cool thing is, in this lecture, we will concentrate on just mass transfer. So we know cooling, this is something which you need to keep in mind. If we have a cooling, that we also need to think of cooling power of the device. But in general, if you dimension a reactor, you have your cooler there. So you would dimension it not just for a very simple process. You will go up and say, my cooler is dimensioned in a way that all regular processes I can think of for this reactor will work. Yeah. So it's not a good idea to dimension equipment that it's just enough for your process. Then you come up with another process and you realize now the cooling power is not enough, because then you have to buy another one. And this is, of course, not so smart. Yeah. So therefore, usually the cooling power is not an issue. This you install once and then it's there. So therefore, we don't care too much about that. Yeah. But the energy then is per process, whether you have a high or low cooling power doesn't matter. The energy you pay for will be the same, whether it's a high or low cooling power. So therefore, it's also, let's say, fair to neglect it. My camera doesn't like Wednesday afternoons. So, therefore, we concentrate today on mass transfer, because this is really important. The oxygen is at the end, it's about oxygen. Yeah. So bringing in the oxygen into our broth, that's, if it's an aerobic process, always the major problem. And there we have to talk about. The cool thing is, despite the fact I said we neglect the mass transfers, but nevertheless, I said, if we look at these laws here, the law heat transfer, law momentum transfer, and law mass transfer, you see that they look all the same. And if you're a fan of momentum transfer, I recommend go to Frank Platte and say, I'm a fan of momentum transfer, and Frank Platte will tell you everything about momentum transfer.
Even though you're not Frank Platte, can you maybe still give a small glance at momentum transfer?
A small glance I can give. The real So the glowing eyes will be given by Frank Platte. So this you have to understand. Why is momentum transfer a bit a problem? The problem with momentum transfer is it's getting very fast, very complex, because these laws here don't take into account the dimension. Yeah. So you are in 3 dimensions, and you want to follow your particle, and this particle then goes to another particle, transfers the momentum to the next particle, and then things rapidly get complicated. And therefore, this is then handled with so-called Navier-Stokes equations, and already these equations look not very nice, and you do then numerical solutions. This is what Frank's company does. Yeah? They can tell you if you inject something in whatever dimension, how this looks like. I have no idea how they do that, but the computer does that. Yeah? So there is a computer calculating everything, and there is Frank and his friends knowing what the computer does. So this is really complicated. This is a completely different story. And it's also not very reasonable to simplify there, because it's like it is. You have your turbid, you have turbulence and so on, and this is momentum transfer. Yeah?
And it has nothing to do with the Boltzmann distribution.
I don't want to say it has nothing to do with Boltzmann distribution. I just want to say if momentum transfer in a bioreactor, that's what we talk about, is that we have our stirrer and how the stirrer then transfers the momentum from the stirrer to the liquid. And the point is, it's always about relevance. So that's the cool thing about a bioprocess person like me. So the relevance in a bioprocess is usually low, because in a bioprocess, it's not an issue how this momentum is exactly transferred. I know what gas stream, you will see that later on, what gas stream and what rotational speeds make sense. This is the input, and then everything is fine. If you, of course, want to know that you build a bridge and you have a river and you need to know what pressure is on whatsoever, you need to calculate that and you need to be able to calculate that. But this is not what we do as users in bioprocesses. Yeah? Okay. So, yeah, heat transfer, mass transfer, and now we go to mass transfer. And there are two types of mass transfer which we have. One is diffusion and the other is convective transfer. And if we have both transfer types present, the diffusion dictates the speed because it's way slower, very simple. Yeah? So the slowest transfer type dictates the speed. And therefore, if I want to calculate transfer times, or if I want to analyze mass transfer, it's fair to neglect everything which is convective, where we also have sometimes momentum transfer in this case, and just look at diffusion, because the error we make with respect to the neglecting the convective transfer is low. Yeah? And this is, of course, there is an animation. This is a 1-hour animation. Are you ready? Then I can press start. 3, 2, 1, go. I repeat. And this beautiful animation exemplifies what you mean. So momentum transfer and convective transfer is just you push the particles through, and diffusion they have to go through by chance, therefore it takes longer. Yeah? Whether it was worth it to do an animation for that, I don't know, but there was some space left on the slide, so therefore space left for an animation, so let's go. So now let's look at how this mass transfer at the end looks like. So if we look at this slide here, and if I look over my mess to find where I am, At least this looks not too bad. So we have here on the board, we see that this is a phase in between. So there is a phase change, and we have on the left side we have a certain concentration C1. On the right side we have another concentration C2. And of course, at these phase borders, the masses can transfer. Otherwise, it makes no sense. Yeah. And we assume that on the left side, it's the concentration is everywhere the same. On the right side, also it's mixed. This you can do. You can put the reactor 1, reactor 2, and the membrane in between, and mix everyone, and then look what's happening. So it's clear that if you plot here the concentration. So this is the concentration, and this is the dimension. Then there is a concentration difference like this in between. So that's obvious. And now my question is, what actually dictates how fast this transfer at such a border goes? So how fast is this transfer?
As big as the membrane pores it out?
Yeah, let's say the membrane is, you have a certain, so the phase border is the same. This you cannot change, it's constant. So how can you make this transfer, or what dictates how much is being transferred per time? Fast is kind of not correct. How much is the transfer rate?
Concentration in C1 versus
concentration and pressure?
Yeah, concentration and pressure. In this case, it's a liquid. If it would be a gas, pressure, yes. So in a liquid, it's concentration. So this means that the higher the concentration is, and the lower at the higher concentrated side, and the lower on the other side. So the higher the concentration difference, the higher the transfer rate. Yeah. Another thing which is relevant here.
Temperature?
Yeah, temperature, but we stay constant now with the temperature. So if you increase the temperature, you can go up with the transfer rate.
Flow speed of the flow speed?
It's the size of the intersection here in
exactly, the area. Yeah. So A. So at very, very simple. So this you can say the transfer rate is the area fold the concentration difference, and of course we will always have some kind of diffusion constant or so, yeah, mass transfer constant. So that's very simple. This is at the end. This is what's behind mass transfer, yeah. So the driving force is the concentration difference, and the area. The larger the area is, the more is being transferred. Of course, if you use a different material at the phase spot, it's clear, then you could, let's say, have there a difference. If you increase the temperature, also this will affect it. If you're of course smart guys, so you know that reverse osmotics and so on also in liquid works with pressures. However, this is of course not something we do in bioprocesses, to be honest. Yeah. So this is if you want to get your distilled water with reverse osmotics, you can also apply pressure to liquids. So and then just you can this with the area is of course clear, and what you would like to have is you normalize that by the area, that you get the flux density, because then you can compare how the diffusion rate is at different conditions, and you can talk to each other, and you need to multiply that. So if you then go to diffusion, you start in principle with the same. You have just not, in this case, you have not a phase border, you look at a differential difference, but that's then instead of delta C it is simply dC dx, and also, so this is the concentration gradient, the higher the concentration gradient is, the higher is the driving force, and of course also there will be a constant, you have, and also there will be then, of course, the area will be in this law. So at the end, the density is here, the gradient, dC dy in this case, in the y-axis, and we have diffusion coefficient, and this is then fixed law of diffusion, which you have certainly already talked about in thermodynamics, most likely, or? Oh, I forgot always my bag. I try to throw it a bit better now.
So what is the difference between mass transfer rate and mass flux? Isn't flux transfer rate? Like the transferring of...
Yeah, that's similar. Yeah. So I wouldn't. So the important difference is density and overall transfer. So this is, of course, here we talk about diffusion, and this is maybe the difference here. So diffusion is not just at one position. This goes then over the complete stuff. But I wouldn't take these figures too serious for bioprocess engineering. For thermodynamics, yes.
So they're similar things?
At the end, it's similar, but of course, diffusion is there's nothing in between. Phase water in between. But you will see later on, as we always talk, we're caring about phase water stuff, so we don't look at diffusion we look at diffusion, but we are always looking at diffusion at phase water. So you'll see we will mainly. Okay, so here we are. So where is diffusion relevant? So you see that if we talk about diffusion, we look at mixing agitation. Of course, there it's relevant. In a normal bioreactor, so what you have done in your KLA experiment, you have a very small bioreactor, and you had a stirrer which was stirring like hell. So the liquid inside had a low viscosity. So do you think that there are areas in your liquid phase where you really had to take care about diffusion? Just liquid? No, not really. So there is this convective transfer in this small bioreactor, this stirrer, at these stirrer speeds, there will be no relevant diffusion. So it might be for the lower rotational speeds that sometimes it might take a bit, but before really diffusion comes into play, still you will have a transfer. You have these eddies will be mixed, and at higher rates it's no problem at all. However, if you go up to larger and larger scale, it's getting more and more difficult to achieve that. And of course, if you go to higher viscosity fluids, even if in a small bioreactor, if you put in honey, for example, and your stirrer, you cannot stir it like this. So there, diffusion is then, of course, highly relevant. So it's not always that in a bioreactor, diffusion doesn't play a role if you just look in the liquid phase. It depends on the reactor. For the liquid phase, we always, for our calculations and so on, we always think of low viscosity fluids, so therefore we make life easy in this case. Okay, now across phase boundaries, you first have to think of what phase boundaries do we have in bioprocesses. And as listed here, we can have in principle 3, and we can solid liquid, liquid liquid, gas liquid. Gas solid in a bioreactor is rare. There you have a problem. If you have a gas solid transfer, then your liquid has been evaporated and something went really wrong. So you don't think of diffusion anymore. You think of rescuing your equipment. So mixing agitation, so mass transfer across phase boundaries. Solid liquid transfer is if you have sal clumps inside or if you have solid nutrients. The processes we look at, you will see later on, we don't have that, but especially if you, for example, in food production or so, of course, this happens. Now, liquid-liquid transfer is, for example, if you, by remediation, if you want to metabolize oil spills and so on. This oil is, of course, not completely solved, and then you have phase borders. Of course, this exists. Or also if you do extractions like liquid-liquid extractions of penicillin, then also this is in bioprocessing relevant. In general, you don't have that in the bioreactor. This is rare that you drive a bioreactor where you have this phase difference. Frank, I'm with Frank Blade. Frank works on reactors, in general chemical reactors, but also now including bioprocesses with several phases, which has some advantages because you could, for example, do extraction processes in parallel. But usually it's hard to run these as a tank reactor, so you run these a different way. Yeah? But in principle, it's not that this is completely stupid to run bioprocesses in another way. Yeah? There can be an intention behind. And then we come to gas-liquid transfers. This is, of course, what you did today in your lab course. This is KLA measurement. This is the transfer of from the gas phase to the liquid phase of oxygen. And this is kind of the bread and butter stuff. Yeah.
So I'm trying to understand what's the fundamental difference between, not the difference, when do we have diffusion and when do we have convective mass transfer at play? Or is it both of them happening at the same time? And what's the principal difference?
Okay, so there was a principal question. What the hell?
Two of them.
Yeah. So again, a convective transfer also always means here in this room you have an aeration. So this air condition pushes the air through the room. So this particle doesn't do what it wants. This air particle, it's pushed through the room. This is convection. If you stand outside and there is wind, this is convection. If you want to bring air in the room and you open your window and it's windy, this is convection. And this is intuitively, if you have a lot of air around, so if wind is around and you want to bring fresh air into the room, and if the wind is outside, 1 minute is enough. If outside the air kind of stands around, then it's the same for you in your room. Then the air really has to come in by diffusion. So this takes way longer to have the complete exchange of the air. So if you took a shower in the bathroom, for example, and if the temperature of your bathroom and the temperature of the outside is the same, just the humidity is different, and no air gets inside and out, then it takes long to get this humidity out. If there is a temperature difference, you will always generate convection because there will be an air flow then, but it's assumed the same temperature, but it's windy, then you just blow in the other air and that's way faster. So that's the difference between convection and diffusion, and the diffusion takes longer. And this is in the gas phase. Of course, the diffusion coefficients in the gas phase are way lower than in the liquid phase. So the diffusion is way faster in gases than in liquids. Yeah.
So it's basically for convection we have some kind of force that pushes a lot of particles in the same direction.
Exactly.
So diffusion is just random motion.
Exactly. Yeah.
But for diffusion, it's only the concentration gradient that's relevant there, right?
Yeah. Yeah. So that's the point. If you have no convective transfer because there is no wind, if you have a high humidity outside and you want to bring the humidity, which is a bit higher of your room outside, if you want to bring it out, this takes very long because the difference of the humidity from in to out is low and nothing is just pushed out. If you have a wind, it doesn't really matter what the difference is of your humidity from the inside and outside. The air is just exchanged. You just blow in new air, full stop. Yeah. So that's the point. Also there you see the driving force. Yeah.
So when you have a membrane, is diffusion greater than convection? Like, is it a stronger motivator for utilization?
At the phase border, it's of course a transport via the phase border. There, usually it's not convection. There you don't push it through. So at the very beginning, what we said, this is just the phase border difference. There, it's just the difference of concentration and just the difference, just the area. This is the same as fixed law, just with a step change. Yeah. So it's a delta and not a D. So that's kind of diffusion at a plane. Yeah.
But if you wanted to make it happen faster, would you use convection?
You need to remove the phase border. That's the point. So if you have your window open, but you have here a membrane where your water can diffuse through, but the wind cannot get in, you have to wait a long time. And even if the air in your room is completely mixed, and outside you have wind like hell, so it's transported away immediately, but still you will have to wait quite long. That's the comparable situation with the phase border. Yeah? And of course, this is something you would not like to want to have there. Yeah?
So in this case, the phase border would be the window, right?
The window now, of course. So a membrane instead of the window. Yeah?
It would matter then how...
The larger it is, the faster it goes, and also there, the higher the difference is, the faster it goes. So if we have an aeration here inside, which just rotates the air, of course, if it's an air condition where you bring in fresh air, makes no sense, and outside there is wind, as soon as you have a membrane here, we have a problem, because then, of course, the wind doesn't get in. Yeah? So the cool thing is that it's not relevant that this air molecule from back there needs to diffuse here. This is brought here by convection because we mix here the air and we mix the air outside. However, at the phase border, this convection, directly at the phase border, this convection doesn't help. So this is the same as we have in bioreactors. In the bioreactor, we mix. So in the liquid phase, no issue with respect to diffusion, because that's, if at all, at very, very tiny areas where it's negligible then, because the contribution there is very low. But as soon as there is a phase border and we need to get beyond this phase border, of course, there this convection stops, kind of. Yeah?
And we'll keep going until both sides have equal constant.
Yeah, this is well, yeah.
Do we need inequality of concentration, or even with equal concentration, some kind of exchange will be happening?
Maybe we go to the next couple of slides. But the cool thing is the questions go exactly in this direction, because what you want to see is what's happening actually at these phase borders. Yeah? And we have a phase border. If we have a transfer from the gas phase to the liquid phase, which is oxygen transfer, of course we have a phase border. Yeah? So, and this is what we want to see. But there is still another question.
We don't always have the phase border with factor, right? Or do we?
Yeah, if we want to bring oxygen in a liquid, in general, yes. There we always have a phase border, because oxygen will be in the gas phase. Yeah, but we will talk about, we have already talked about that. You see that you could also think of that your nutrient has a low solubility and is in solid form and needs to be transferred into the liquid. Then of course we have a phase border from the solid to the liquid phase.
So even in diffusion we have a phase border.
Sorry?
Even with diffusion we have a phase border.
I would say we go on. So we look at solid-liquid transfer. We don't look at liquid-liquid transfer where we have extraction. And I think it's getting clearer now what I say. So maybe I go back to our example here. So the point is, we said that there is here our membrane. Yeah. So the outside wind, here is wind. So with gases, everything is fine. But if we would now be in the liquid phase, which would not, of course, not good because we're not fishes, but it looks like an aquarium. So therefore the model is not so bad. And you mix and you mix and you mix. It is certainly difficult to really mix directly at the phase border. Yeah. So it's easy to mix in the middle, but the closer you get to the phase border, the more difficult it will be to mix. At least if you're in a liquid phase. In a gas phase, you would say this is not really an issue. So the point is, the central topic of this two-film theory is that if you have a phase border between two liquid phases, that you say at the phase border you will always have a liquid film on the phase border. Yeah?
Did you read that? What did you say at the last?
I said that on the phase border, you always will have a film, where your convective transport cannot get there. Yeah? The faster your mixer is, the smaller this film is, so you can change the thickness of this film by changing, for example, your mixing intensity. So if we have a mixer, we are now in liquid, and if we have a mixer, and this mixer mixes slowly, and we have something, so for example, a dye on the top of the surface. So if this just slowly mixes, you almost don't see anything here. The faster you mix, then you will see then, also it gets to this color. So you can change the thickness of this film by changing your stirrer power. Nevertheless, you will never ever get directly to the phase border. Yeah? It will be smaller and smaller, microscopically smaller, but you will not directly get to this phase border. And this helps us if we think like this. So this is the two-film theory, and my camera wants to stay at the phase border. So this means that if I look at two phases now, in this case liquid phases, phase 1, phase 2, where I have two different concentrations, then I say, I have here and here I have ideal mixing, so transport by convection means ideal mixing. But the closer I get to this phase boundary, then I will meet the problem that there will be a film on this phase border, and in this phase border I cannot mix by convection, so therefore I will have diffusion on this film. Yeah? And this of course happens then at both phase borders, and the thicker the phase border is, the larger the area is where I have diffusion. This is a two-film theory that's very important, because this is not necessarily always that you want to measure that and the thickness and so on. It's just something which helps us later on to mathematically describe transport processes, because at the end this is what we want to do. But there was a question.
I mean, you kind of answered it already, like the sigma stands for the thickness of the films, right?
Yeah.
Yep. I'm a little confused by this word phase border. Why can't we just call it a membrane? How is it different from just a normal membrane?
Because if we talk of a gas-liquid phase border, it's not a membrane.
Okay.
A bubble or if you have your Erlenmeyer flask and you have your gas above, there is no membrane, but there is a phase border. Yeah. Oops. Okay. So now, of course, I'm just looking at the watch. You can look at how you can describe this mathematically, and the easiest thing to do that is looking at the solid-liquid interface. Yeah, we're more interested at gas-liquid, but still solid-liquid we should not neglect. And if we look at this here, of course there's no mass transfer within a solid. Yeah, solid is, for example, a crystal and so on. So the transport starts at this solid-liquid interface. Now, if we look at the surface of the solid, and now this is important, and I wanted to draw that on the board, but as it's now already there, we can have a look there. This is, by the way, the problem when I do lectures hybrid, that I don't have my preview screen, so I don't know what slide comes next. And if I know what slide comes next, then I say, this I want to draw on the board. But now I click and say, this I wanted to draw on the board, and it's always too late. Okay, yeah?
Just a simple question, what does CGR stand for?
CGR, this is cool, because this comes from, I see this, I think I have from a textbook, which is a German textbook, and this is C-Grenze, and should be C-border. So it's C-border, that's a good question, C-border. So this is the, at the border of the solid, liquid phase. Now on the top of so always the question is, of course, always, what is now the concentration? So my concentration in the liquid phase is my concentration in the liquid phase. That's clear. This I measure. Yeah. So, and I want to know now the driving force is, of course, the difference of the concentration, which is exactly at the surface of my phase transition versus the concentration which is in my liquid phase. The concentration in my liquid phase is all over the same because I defined it like that. I said we mix perfectly. So I just need to consider what is actually the concentration on my solid phase. And of course, if I have diffusion, this means that on the surface of the solid phase, CGR, I am in an equilibrium. By definition, otherwise it would make no sense. And therefore the concentration at this position has to be the solubility of the substance. Yeah? So directly next to the phase border of my crystal of salt, for example, I will have a concentration which is exactly the concentration which I can achieve with the solubility. And then I have this area where I have my film, and then comes the concentration of my in the liquid. And of course, the larger this distance is, so this gives you my delta C. This is the concentration gradient, and the larger this distance is, the longer it takes, because then the diffusion constant gets in. Yes.
That just reminded me of a question for the liquid-liquid transfer again. Does that basically mean that the different sigmas also give the different solubilities of the two phases in each other?
No, this is so you mean that so you mean here the size of the thickness of the film, or what? Or what?
When we have here at the border at the solid-liquid interface, the solubility of the solid in the given liquid, then I think it's reasonable to think that when we have a liquid-liquid interface, then this interface is always also dictated by the different solubility.
Okay, at the interface, yeah. But
so they're basically the same.
Yeah, but let's start now first with this interface, yeah? Okay. So here we are, solubility. So this is the, so there you, because a bit, we will come to that if we look at the gas-liquid interfaces, yeah? So here we say it's the solubility, makes sense, and then if the closer you come to the solubility, the longer it takes. In other words, if you very simple, if you, let's say, solve salt in water, and the concentration of water, of your salt in water at the beginning is 0, at the beginning it will be fast to solve it, your concentration will quickly increase, but at the end, if you come close to the solubility, it will take longer. Yeah? This is what this says, because the concentration difference then decreases, and the driving force, the transfer rate goes down. So, and this is just going to this equation. You have your delta C, you have your transport coefficient, and of course, you have your surface. That's always in this equation. And this is the same as we have shown at the very beginning here at the board. And this concentration difference, again, is the difference between the solubility minus the concentration in the liquid. And of course, the solubility is a function of the temperature and so on. Don't forget that. Yeah, we have, it looks always like constant, but again, of course, if you change the temperature, you will change also the solubility. The solubility is, of course, also a function of what liquid you use. That's also clear. Yeah? And this transport coefficient is the quotient of the binary diffusion coefficient divided by the thickness of this membrane. This sounds not, of course, now mathematically cool, because then we can say, we can calculate the thickness of the membrane, but in reality you have to measure it anyhow, so you will experimentally determine it. You have always determined KLA, so although there the thickness goes inside, nobody has ever determined, or maybe they try to measure it, the thermodynamics guys, but at the end you don't care what the actual thickness is. You want to know the complete coefficient. Yeah. Okay. This is solid liquid transfer, and now we come to gas liquid transfer. That's what we're interested in. If we look at this, we first need to think of how does this oxygen at the end come to our cell? And the answer is very simple. So first of all, it's in the gas bubble, the oxygen, with a high concentration. Then it needs to go to the liquid, and there will be a liquid film on the phase border from the gas to the liquid. Now my question is, in the gas bubble, I always talked about there is convective transfer. Within the gas bubble, do we have convective transfer? Or in other words, have you ever seen a stirrer in each gas bubble? Yes? Yes, you should change the drugs. They're not good for you. So in a gas bubble there is no convective transfer. Problem. Internet help us. We now are at a stage where we already say, in the gas bubble, no convective transfer. So the question is, what?
But gas particles always collide with each
Yeah,
other, so like
it has to
kind of
hold
creates.
It doesn't have its own convection current in the system.
Yeah.
Not necessarily, yeah, because if they freely flow inside, whether this is really a convection, I'm not so sure.
No. Would it not be like a microconvection, if anything?
I'm not so sure. So of course there can be some convection inside, but so we're not so absolutely relaxed with respect to convection in a gas bubble. If someone looks deeply in our eyes, where is the convection there? It's kind of constructed. And we heard the word Pfusch in the last lecture. Yeah? Germans, again, don't like that. So in other words, in this case, Pfusch means, Mr. Gavenda, that we would have to calculate diffusion in gas bubbles in 3 dimensions. Do we like to do that? No. So we need to find a reason why we can neglect that. If you find a reason, then we will neglect that. I listen to you.
They're already small enough, so it doesn't.
Small, yeah. Small is good. Small is good. Yeah. So that's like in Germany. Saarland, small, neglected. Yeah.
Maybe we can assume perfect concentration, dispersion in a given bubble.
But again, there is no stirrer inside. This is exactly our problem. Small is good because if you say it's small, then we say, if our gas bubble is like this room, then we would start to say, ooh, if there is no convection at all, because we know that it takes a while until if we open the window and there is no real exchange until we get air over there. So that's our experience. But we say if it's so small, small is good. And the other thing is, which goes a bit in line with small.
Can you maybe repeat the key question once again?
The key question is we are not Frank Glatte and we don't want to calculate around in these gas bubbles. Because for us this is not fun. Therefore we need to find a solution how we can argue if Frank talks to us and says, but you cannot neglect it, that we say, we can neglect it because small
and slow.
What? Sorry?
If they're so slow that they have enough time to diffuse.
But slow is bad. We don't want to have it slow. We want to have it fast.
I mean the concentration difference between the interface and the inside.
Maybe we go back to the internet to this slow argument.
Relative surface.
So at the end, we are here in a gas phase, and at the end, we are then later on in the liquid phase. And we already said the gas bubble is small. Yeah. So, but in other words, we have the feeling that there is diffusion happening in this gas bubble. Yeah. So we are not really talking about convection. But if we now compare diffusion in gas and in liquids,
Probably becoming faster in gas.
it's way faster. It's order of magnitude faster, thousands of times faster. So, of course, diffusion is a slower process than convection, but it's way faster in gas than in liquids. And if these gas bubbles are a couple of millimeters or so, what we have in a bioreactor, we don't have gas bubbles of meter cubes, then it's no problem. And if these are so large, then it's true. Then we have collision and so on. Then we will have real convection also brought in this gas bubble. So we're happy we have rescued ourselves. We have a good argument if Frank Platte tells us you should calculate that. No, we don't need to. So therefore we can neglect that. This is cool because then we don't need to think also of films and so on in this gas bubble because we can neglect all this. Of course, it's diffusion, but we don't really care because this is fast. So we only need to take into account the liquid film on the gas bubble where it's diffusion. And now, of course, it depends on where our cells are because we need to get into the cell at the end. Don't forget that. Yeah. And of course, if our cell is happily as a single cell, the cell is very small. Being small also helps. So if there is a liquid film around the cell, as the cell is small, this liquid film will also be very small compared to the film around the gas bubble, which you really see, which is macroscopic. So this we can also neglect, which makes us happy. However, of course, if it's no more a dispersed single cell, but if we have agglomerates of cell, then things are different. Then, of course, we need to first get into this agglomerate, especially if they form capsids or whatsoever, so a gel around or so, then it's just diffusion. And the other evil thing is, then it's of course not an even distribution. So the outer cells, there will be a different concentration than in inner cells, and there will be a different driving force. In this case, of course, we cannot neglect it. So this is the reason why we always put the stirrer at a speed that we don't have that, because again, we hate calculating around in these conditions. Could you imagine a bioreactor where you say this is the normal condition? So where this the cell is not dispersed. So where you say, aha, I have agglomerates of cells and I want these agglomerates of cells.
Perhaps anaerobic.
You also don't want to have agglomerates.
Complex
but the cool thing is in
like,
an anaerobic reactor, we don't need to care about oxygen transfer. Sorry?
Maybe biogas reactors, where you really have quite complex reactions?
Yeah, but also there in a biogas reactor, we don't talk about oxygen transfer. What?
Well, we have to fermentation.
Yeah, but this is usually always what we want to do. So we're now, of course, in an aerobic reactor, so it's not formally fermentation, but still we're in a bioreactor.
Mammalian cells, because we can't mix them?
Yeah, the cool thing about mammalian cells is you cannot mix them as good, but the oxygen, you will see later on, their oxygen demand is lower because their uptake coefficient is lower. So therefore, you don't need to transfer as much. So that compensates that a bit. Yeah.
When we want to recover like enzymes or something like that?
Yeah, and what we do there?
We use adhesion. surfaces to tell that?
For example, so we immobilize, for example, cells. So we have a bioreactor where we have immobilized cells, and usually then you put them in a resin of, for example, agarose. In this case, of course, they are no more dispersed. And of course, if you want to dimension such a reactor with respect to oxygen transfer, you have to take that into account. So there you cannot neglect it anymore. So there are, of course, operation conditions where you need to do that. Yeah? So simplification is okay, but you need to know when you have to stop with simplification. That's not a nightmare. In this case, you just have to take that into account. It works, of course, but you need to remember this. Okay. Oops. Now, as we have already forgotten to draw things on the board, we can go right ahead and look what that means for oxygen flux densities if we look at the gas-liquid transfer, if we look at oxygen transfer. We have said that this is the gas phase, this is the liquid phase. In the gas phase, you also always talk not about concentration, you talk about partial pressures. And here, of course, the pressure directly goes inside. Yeah, just concentration makes no sense because there the pressure directly goes inside. We all agree that in liquid phase, if your pressure is like hell, then things also get different. But at normal conditions, this is not the case. And now, at the phase boundary, this is coming back to your point here, there Henry's law applies. So also here at the phase boundary, we're at the saturation concentration. And this saturation concentration depends on the concentration in the gas phase and the Henry's constant. Yeah. So that's similar to what we have done, by the way, in the anaerobic experiment, how our ethanol measurement principle looks like, yeah, in equilibrium, similar. So here, this concentration in the liquid phase is the saturation concentration of oxygen in our gas phase. And now, wait a second, now comes the trick that we say that in the gas phase, this film here is something we can neglect. We all agree, because this is gas phase, this has to be small and can be neglected in contrast to the liquid phase. So we can say that this partial pressure or equal to oxygen concentration at the phase border is more or less the same as the partial pressure in the gas phase itself. So this helps us because PG is then PGI and we neglect everything on the left side. We just have to concentrate on the right side if we want to calculate transfer rates. But there was a question.
Yes, so this is not a function of the liquid anymore, right?
Why is this not a function of the liquid anymore?
Because we said before in liquid-liquid transfer that obviously the solubilities depend on the kinds of liquid that we use, and I don't see a, how do you say, some reasoning of liquid there.
Is it really true?
You tell me, that's my question.
Is that not a function of the liquid? I'm asking you.
So, what was the question?
So the question was, so I have a gas phase, let's assume gas phase is air. Let's keep that constant. And now the question is, if I have a different liquid phase, if it's not water, does that change? Yeah, for sure. The solubility of oxygen in another liquid will be completely different. Yeah, for sure. There you will have a different Henry's constant. Yeah? This Henry's constant is a function of temperature. This function is a function of the liquid. It's a function of the element you're looking at. Yeah? Henry's constant will be different for nitrogen and so on. Yeah? So of course it's a constant, but a constant for oxygen to transfer gas liquid to if the liquid phase is water. Yeah? But you have, of course, liquids where the solubility is different. And if you have a liquid with a higher solubility of oxygen, then and the same concentration at the end, then of course the transfer rate will be way higher. That's clear. Yeah? you can better solve it. So it's faster to solve it. So this means also if you have, in reality, if you need to solve something which is hardly soluble in a solution, even if you have a large volume, it takes very long to solve it. This is the problem, because the driving force is very low. Yeah.
So when we're looking at this gas phase to liquid phase, is it not in a circle? Because it's a bubble. So we would have, like, what is the actual outline of a bubble then if you have the gas phase?
That's a very good question. So you talk about the area. What is the
what is the actual area of around the bubble that is?
We keep that question in mind, but this is of course a not too bad question. All questions up to now were good. Yeah. Of course, also the questions from the internet were good, and the contributions of the internet were good. But again, the cool thing is now we say gas phase we can completely neglect. So we just look at the liquid phase and what's happening there. So at the end, we can just copy. If we want to know what is the transfer, we can just look at this equation there, which gives us the flux densities, and say, okay, what is the flux density at the liquid phase? Well, the flux density is Q0 is equal to, maybe I'm not really in the middle here, I'm too much in the middle. So the flux density is, easier to look at this sheet here instead of the QO for oxygen now, of course, not for a general term. QO2 is our constant. So this is the first equation I just copied. Yeah. So this is what we have developed at the very beginning. So what I just wiped out. Yeah. Because we have said we neglect everything in the gas phase, and therefore we can just go with this first equation. KL fold A, the area, fold the concentration difference. And I said the concentration difference is C.
L initial minus L.
What?
Liquid initial minus concentration of liquid.
So K is just the transfer coefficient in the liquid phase, KL. Yeah? So that's the constant. This initial constant, so this is now I wiped it out, of course. I was too early. I should have put it. So this is phase border equation. Yeah? What we had at the beginning. We had this constant. We had the area. And the concentration difference. And the concentration difference is the saturation concentration of oxygen in our liquid minus the actual concentration in our liquid. L stands for liquid. Yeah. So this is, at the end, the oxygen flux in a bioreactor. This is how much oxygen is getting into your bioreactor per time, flux. And now, the point is, if you look at this value, so you have your bioreactor, and you say, okay, I'm getting this now into my bioreactor. Now you want to compare that, of course. So how much oxygen is getting in your reactor? Is that a lot? Is that little? And so on. So if you have now a bioreactor, so this is the complete oxygen flux in your bioreactor over the complete bioreactor. And it's of course clear that if I have a bioreactor which is very large, it's not too surprising to have then a high oxygen flux in this bioreactor. If I have a bioreactor which is very small and I observe a small flux, this is also something which would not surprise me too much. So it's reasonable to take the volume of the liquid phase into account. Yeah? So, and this is when we come to the oxygen transfer rate, where we take the volume into consideration. And
What is the unit
So the unit here is, it's always a transfer per time. So for example, kilograms per hour. Yeah? Or if it's smaller, it's moles per hour.
Because density doesn't have to change in the units.
Sorry?
Because it's I don't know, I thought the word density would have something to do with change in the units.
Yeah, this is not the density because you have the area here. Yeah, if it's per area, then you have per meter square. Yeah, then it's a density. Yeah. Okay, so just going back to this, and then we can say, okay, if I normalize that to the volume, I have my oxygen transfer rate because this is reasonable. So my oxygen transfer rate is my oxygen flux divided by the volume. This is the oxygen transfer rate. And I do that in order to make that comparable. And this is equal to KL, I'm just copying, fold A divided by the volume, fold C star minus CL. And then I just write this A divided by the volume is then my little a, KLA, fold C star minus C volume. So this is my oxygen transfer rate. So, and this is, of course, a value which makes things comparable. Yeah? Because if I have an oxygen transfer rate in a reactor of 0.2 per second, what does it mean? Well, it depends on if I have an oxygen flux, I don't know what amount of oxygen is really going over if I just look at this QO2 in my little dimension. But if I have this normalized to the volume, then I really can compare it. Yeah? Very simple. And this is this KLA we always talked about, and this is the KLA you actually measured. Now we just come to this equation here, and A is at the end the gas-liquid interface. And this was exactly the question you asked at the couple of minutes ago. This is not so easy to measure. So we have two problems. In all these equations, we have this thickness of this film coming from the two-film theory, which goes, of course, into that, because we have a tabulated diffusion coefficient. This is something which can be measured. So you have a pure diffusion process and measure this diffusion coefficient, and then we have this thickness of this layer, and then we have the area. And how can we measure that? So an area, so we have now the bubbles sparging in our bioreactor, and we have a complete turbulent dispersion of the bubbles in our bioreactor. And now you want to measure the surface area.
The formula of the surface area of the bubble.
Yeah, but you would have to have an exact distribution. You need to know an exact distribution of the bubbles, which can change over time. Hard. And at the end, the question is, do we need that? This is the question always. But there is another question. And this is a bag question, because I just see that my poor bag was never again thrown over the...
I actually don't want to ask a question. It should have been more like an answer. Yeah, like, doesn't this sparger basically say that there is like a maximum bubble output or like a diameter of bubble the sparger produces that we can take as an average?
That's a very good question.
Yeah, more the question, yeah.
And the good thing about this question is, as you did today the experiment, this question goes back to you. Of course, to all of you. Also the friends and the internet who tried to relax from the KLA experiment today. So what we heard is that at the end, the bubble size is a function of the sparger. Yeah? So if I vary the sparger, if I make smaller holes, for example, in the sparger, I have smaller bubbles. So at the end, why should I really care about that?
also have a mixture which is going to break down bubbles too.
Yeah. So first of all, your mixing process will result in that you break down the bubbles. Yeah. One thing. And the other problem is that bubbles try to fuse. This is called coalescence. And this is what you don't like to have. So in principle, you're right. So if you have a sparger, and if you then, after the bubbles came out, have a condition where you are sure that these bubbles never ever meet each other, everything is fine. This will not happen. They will meet each other. And as soon as they meet and start to fuse or something like that, then you have a change. And therefore, if you have, of course, an air-lift reactor or so, the only thing determining your bubble size is the sparger. But in an air-lift reactor where you have no stirrer, measuring KLA stuff is even more difficult than in still tank reactors, because your distribution of bubble sizes is completely uneven, because you cannot prevent this fusion of the bubbles. This is the problem. So therefore, the sparger in a still tank reactor has only little influence on the bubble size distribution. The stirrer has a large influence on bubble size distribution. Yeah?
Could you make an example of a situation where we need to use the oxygen, like calculate the oxygen flux as one where we have the oxygen transfer rate? Just like to understand the different uses.
Now again, the oxygen flux is over the complete reactor. So if you balance everything, of course, you take the volume into account. You will see that later on in our examples. Yeah? So and you have then the consumption rates, for example. The consumption rate is there more interesting. Yeah? So you will see how that then goes all together. Yeah? Examples will come. So a very big problem with oxygen, of course, is that the solubility of oxygen in the liquid is low. And this, of course, doesn't make us too happy, because this means that we cannot put in the oxygen at the beginning, close everything and wait. So this means that even we have to provide all oxygen which is required. It is consumed within seconds. So if you stop your oxygen in the reactor, if you have a reactor where you have a high cell density and quickly growing cells, will be consumed within seconds. This is also the reason why with the Erlenmeyer flask shaking culture, as soon as you reach reasonable cell densities, oxygen transfer quickly becomes limiting. Yeah? This is the reason why you have a bioreactor and don't always put something on the shaker. It's not the reason why. But oxygen transfer is what you can it's way better in a bioreactor than on a shaker, yeah? Because you have higher surfaces and so on. Yeah? So you need to transfer the maximum possible amount of oxygen 10 to 15 times a minute. And this is not easy. So therefore, your design of a bioreactor is all driven on that. So mass transfer makes us happy because we think of how this oxygen is being transferred, and we already said that oxygen transfer is not so easy because the solubility of oxygen is so low, which is a problem. Now, what factor actually affects the oxygen demand? It's here, and it's kind of obvious. So, of course, at the end, the transfer of oxygen, if you have a sterile liquid and you sparge in oxygen as hell, the oxygen transfer after an hour will be 0, because your oxygen concentration will be the saturation concentration after 1 hour. So the oxygen transfer, of course, needs two things. One thing is the transfer of your oxygen from the gas phase into your liquid. And at the same time, there must be something consuming your oxygen. And of course, your microorganisms are the ones consuming your oxygen. So therefore, it's important that you consider this rate of how oxygen is consumed. And of course, how much oxygen is consumed, or in other words, the rate at which the oxygen is consumed, depends on the cell species, growth phase, carbon source, and so on. Yeah? And then you can say the rate of oxygen transfer follows, of course, again, this relationship. And this is something which comes not as a surprise to us, because this is the same as the substrate the specific substrate transfer rate, specific growth rate, or whatsoever. The oxygen uptake per volume is the concentration of the cells and the specific oxygen uptake rate. Full stop. And of course, this Q0 is a function of time, because the specific oxygen uptake rate depends on the growth phase where you are. And of course, the cell number also depends on time. So therefore, obviously, Q0 is also a function of time. So in other words, you don't need to provide the same amount of oxygen. You don't need to guarantee the same transfer rate of oxygen throughout the complete culture. If you start with a very low cell concentration, the oxygen which is being consumed is very low. So of course, in this case, you also need to transfer very low amounts. Yeah? At the end, if you have high cell density, things are different. Yeah? So in other words, this is how you can then look at that. So we have here different cells. This is an bacterial cell. I have already put that. Bacterial cell, plant cell, and animal cells. And you see that here I have the oxygen transfer uptake rate, the specific oxygen uptake or transfer rate, and the cell concentration as a function of time. There is a question.
Quick question this time. Maybe I should have already known this, but is there any downside for the cells being exposed to too much oxygen at a time? Is there something like oxygen stress?
Yeah, it depends on the cells, of course, but usually the cells you use in aerobic culture, they have no problem with the saturation concentration of oxygen in the liquid. If you are microaerophilic, then this would be a different story. But usually you rarely see production scale cultures of microaerophilic organisms. So therefore, usually you work with aerobic organisms and they can stand the full saturation. They're happy. Sorry?
Due to practical reasons, we don't work with the
microaerophilics are usually chemolithotrophs, and they grow so slowly and so on, so therefore, usually you don't use them.
We have a value product.
Yeah, but in general, what you want to produce is you want to produce your, for example, your enzyme or whatsoever, and using a chemolithotrophic organism for producing an enzyme, rare. Yeah, makes no real sense. So usually you will always try to go to standard production cell lines. Now, if you look at this chart, and if you compare now Streptomyces, these bacterial cells, versus mouse hybridoma cells. So what would you say is that let's say guaranteeing a substantial and a high enough oxygen transfer from your gas to your liquid more problematic? If you look at these charts here. Of course, also the internet is always warmly invited. The number of people in the internet should have exploded because some people left us to the internet, we heard. The other way around, this is also strange. The diffusion didn't work in the other direction. So no internet people diffused inside here.
We have a leak. Maybe the boundaries.
The assumption is we have a leak in the direction of the internet.
Or the boundary is very big.
Yeah, that's also possible. So question, where is it? Where do we need to transfer more oxygen? Where needs the oxygen transfer rate higher? Because the uptake rate is higher.
The last one, animal cells?
Sorry?
Animal cells?
The animal cells, so more here?
Oh.
Yeah, don't forget to look at the scales. The scales are different. Yeah, scales are completely different. So of course, in animal cells, usually you have not such a problem. The problem with animal cells is stirrer. You cannot put in a stirrer like for bacterial cells. So if you would have done the kale experiment you did today, where you sparged in nitrogen, and there were no cells inside, and then you had your stirrer stirring like hell. And with a higher stirrer speed with 1000 RPM, for example, if in this case you would use animal cells, these cells will be vortex. So then you have, how is it called, Thermomix or something like this, where you then prepare your food. So the cells will not survive that. So that's the problem. However, it's not such a problem because the transfer rates you need for these cell cultures for animal cells are way lower. And this is what is depicted here. But what is interesting is that you see that it's not necessarily, so it's not the oxygen uptake rate, which is this open circles here. It's not necessarily the highest at the very end. This can be also highest in between, depending on the growth stage. So it's very important that this is not necessarily constant, this variable. And you see in these charts, it is not constant. However, if we use that for our calculations and so on, we nevertheless assume that it's constant and there is a question.
I'm sorry, I haven't really grasped what the difference between oxygen uptake rate and specific oxygen uptake rate is.
So the specific, this is this chart here. Oxygen uptake rate takes into account the specific oxygen uptake rate and the cell concentration. Because it's evident, the more cells you have, the higher the oxygen uptake rate at the end is. This is the same for the growth. Specific growth rate is a cellular feature. So, but at the end, how many cells you produce also depends on how many cells are present. So if you have a doubling, 1 gram cells at the beginning, and you double, you have 1 gram cell produced. But if you have 100 grams, you produce cells at the beginning, you produce 100 grams. So this is a difference. And of course, also what you need to transfer in as oxygen depends on both. Yeah? How fast the cell breathes and how many cells are around. Bless you.
Thank you.
Yeah? Okay. Now, it's obvious that this oxygen uptake rate depends on the cell and the nutritional environment. However, if the oxygen concentration gets too low, then there is a dramatic drop in the uptake rate. So in other words, you don't want to have your oxygen concentration go lower than this value, which makes us a bit sad because the driving force, of course, of our transfer is the lower this concentration is in the liquid phase, the higher the transfer rate is. Yeah? But we cannot go close to zero because then our uptake of the cells will also go down.
Does it sometimes happen that we are limiting the oxygen on purpose because the bacteria or cell or whatever is then forced to produce more of a value product that we want?
Yes, but this is then of course a special demand. So for example, if we produce a vaccine based on our strain Salmonella typhi 221, which is our standard vaccine strain, you do that. You starve that with respect to oxygen and nutrients because this is then a stress response you induce, which changes the biochemical composition of the surface proteins and increases the immunogenicity. But of course, this is then special. In general, what you want to have is as good as possible provision of oxygen. Yeah? So you design your reactor in this way, and of course, if you have special things to do, then things are different. Yeah? So of course also the substrate has an impact on the oxygen consumption rate, and we remember that if you have a substrate which is highly reduced, the energy content is higher, then the oxygen demand is also higher, and also the rate could be higher, but the rate is not just the yield. So this is when we talked about mass and electron balances, we always looked at yields at the end. So that we say if we have a higher biomass yield, if we have a higher degree of reduction, it's also about rate. So then, of course, it depends on how fast the enzymes are, how fast the uptakes are, and so on. So it's not guaranteed that a higher degree of reduction is at the same time a higher specific oxygen uptake rate. Yeah. So this is not one-to-one, but however, it depends on that. Yeah. Okay. Yeah, so this is what we have already talked about, and this is, I don't repeat that again. And now the point is, the rate limiting step we agreed upon is this diffusion through this liquid film around the gas bubbles. And now we can say at a steady state, of course, if your microorganisms grow at steady state, they will consume the oxygen at the same rate as the oxygen gets inside, it gets transferred from the gas bubble to the liquid phase, which makes sense. Yeah. So if you measure your oxygen concentration in a running bioreactor, you will see that this remains constant. This oxygen concentration in your bioreactor, which is usually measured as a % of oxygen concentration, yeah, saturation. And therefore, if this happens and there are growing cells inside, this means that the same needs to get in as it's being consumed by the microorganisms. Or you could put that, of course, then in a formula, which is this one here. So this is the KLA fold C star minus CL. So this is the transfer from the gas bubble to the liquid phase. And this is what we said, this is the consumption in the microorganism. Yeah? So why is this equation now so interesting? Because we can, of course, if we dimension a bioreactor, and of course we are aware that Q0 could vary, but if we pick up a reasonable QC value and just assume this is now constant, and we have certain conditions, we can of course estimate what, if we end up with a certain biomass concentration at the end, we can estimate what KLA value do we need in order to guarantee, or we can also estimate how much oxygen, or if we have a certain reactor setting, so you have measured the KLA value today, and this KLA value was of course measured independently of cells. Your reactor design allows at a stirrer speed of 1000 RPM a KLA value with a gassing rate of whatever 5 liters per hour, allows a KLA value of XY. Yeah? And this is the highest possible KLA value. This has nothing to do with consumption. You've made this with the dynamic method. So you have determined your KLA value with your equipment, and you know you cannot go up anymore with it because this is the equipment you have. We will not buy if you come with your genius bachelor thesis and you tell me, but I need a different bioreactor because this bioreactor will not be able to do the KLA. This we cannot do, so we just have that. But what you can do is you can say, okay, if I have that KLA, what is the maximal biomass concentration I can achieve with that? Yeah? And this is very simple. So I can directly use this equation here because I can say, in this case, this one, because I can say the maximal biomass concentration I will obtain when this term here gets maximal. Now I said the KLA I have determined, I cannot change. The oxygen concentration, saturation concentration, also I cannot change if I don't increase the pressure also. So I have it given at a certain temperature. But I say, okay, the C liquid, the minimal C liquid is 0. Of course, the Q, we know that the Q0 then is greater, but it's 10% of 0 is also almost 0. So we can say the Qx max, I'll write this in a different line, at CL equals 0, we can calculate this X max. So we say KLA fold C star is Q0 fold X max, and therefore, very simple, X max is equal to KLA fold C star divided by Q0. And this little equation here gives your, maybe it's better to put that a bit down. So this equation here gives you maximal supported cell density in a certain setting. You cannot go higher, because then after this cell density, oxygen transfer will get limiting. Can you grow the cells then any further after the cell density? This question, of course, also goes to the internet. No. Internet. Can you grow the cells any further if you're above the maximal supported cell density? But we wait first for the internet, whether there are.
It's not like they will die all at once. They will say, what did he say, right?
Yeah, I want to grow them. So the question is not that they die. I don't think that they will die because you still put in oxygen and so on. But will they be able to grow?
I mean, that obviously depends on the microorganism and its metabolic abilities.
Or living cell count should liquid.
Sorry again?
The amount of living cells should kind of stay the same.
Yeah, but the point is, what this says is just that below this value, oxygen is not limiting. But you have another factor, which is the substrate concentration. And we will, if we talk about kinetics, we remember we had always said in batch culture, substrate concentration is limiting. However, the specific growth rate is not limited by the substrate concentration. As long as the substrate concentration is high enough, the specific growth rate will be at a maximal at mu max. Yeah? And as long as the substrate concentration is limiting and not the oxygen concentration, this just means that at these phases I have exponential growth. As soon as my oxygen concentration gets limiting, I have no more exponential growth, but I still provide oxygen to the cell. Of course, they then can still grow. However, no more exponentially. Yeah? And therefore, of course, my x is equal to x0 fold E mu t, for example, are no more valid anymore. So if I want to calculate batch times and so on, I cannot do that anymore with these equations. So this means this equation just tells you after this value, you cannot provide the oxygen in the same speed as the cell requires it. Oxygen becomes limiting, and therefore you have no more exponential growth. So it's not yet that the cells die, for sure, and it's not yet that the cells don't grow anymore at all. It's just they don't grow anymore exponentially.
How do you find this saturation constant?
This is tabulated. Yeah, so usually you use the saturation concentration of oxygen for water. Of course, in the medium it's somehow different, but the difference is maybe 10% or so. Ideally, you measure it. Yeah? So this you can, of course, do.
But there we assume that we have strict aerobes.
Yeah, of course, these are organisms which metabolize oxygen. Otherwise, they wouldn't consume it. So oxygen consumption rate of an anaerobic organism is?
0, but I mean there are ways, there are like many metabolic pathways certain organisms could take to still maintain the exponential growth, even though this is limiting.
Okay. So of course you could switch to another substrate. You could use nitrate as electron acceptors. We talk about bioprocesses here. Yeah. So if we design a bioprocess, then and with oxygen, we don't at the same time put tons of nitrate in our bioreactor because we say, maybe if we have
the KLA won't be enough if we want to grow.
Yeah, but on nitrate, the specific growth rate, if you switch from oxygen to nitrate as an electron acceptor, your growth rates will go down. Yeah, they're lower. So this is something, therefore, you don't do. Therefore, you use oxygen. There must be a reason. Otherwise, it would be way easier if I could use my E. coli and put a ton of nitrate at the very beginning. This I can just put in like this. Then I would be happy, but this doesn't work like this.
I mean, yeah, for example, with the nitrate, but with the Crabtree, for example, when the oxygen gets limiting, they also switch to a more favorable.
But that's another point. So in this case, so that's a very special case, that's yeast. That happens as high concentrations, and this is because the rate of uptake of sugar and metabolizing of sugar is so efficient that the respiration is less efficient. But this is a very special case. Yeah. And there it's about yields. This is also what you did in your fed batch simulation. The problem is, of course, then your biomass yield goes down, nevertheless. Yeah. So if you want to produce biomass with yeast, you don't want to have this growing in this Crabtree effect, because this consumes your substrate for something else than biomass. Okay. For producing wine and so on, of course, the Crabtree effect is important. That we also agree. So, yeah, so this is one thing we can deduce from this equation, but we can, of course, also deduce what is the critical KLA if we need a certain biomass concentration to achieve at an exponential growth. What do we need there? You will see later on a typical thing for the design of a bioreactor is that at the starting point, you calculate what is my maximal supported cell density, because then you can calculate the next step, how long does it take to achieve that, and there you can take these exponential growth equations. And then you can say, okay, and now I keep my reactor for 2 days at a production, and I produce, because I have a high cell density, and I produce then my antibody, for example. Yeah? So there might be a growth of, they might grow again in these 2 days, factor 2 or 3. That's not my interest, but I have it at a very high cell density, so therefore I have a high productivity. You will see later on, if we talk about design of bioprocesses, the problem is, of course, that the cells at these conditions are not necessarily very happy, because you have a very high cell density, limited amount of oxygen, and usually this is stress for the cells. So the secret is to keep the cells alive. But if you can prolong this time where they're happy at a high cell density, for example, for producing monoclonal antibodies, then you would do that. Yeah. So your intention is the primary intention, depending on what you plan to do. If you don't want to produce biomass, but if you want to produce, for example, a monoclonal antibody, is not to be always in the exponential growth phase. It's to have the highest possible productivity. And if your product formation is independent of growth, what is the case for a monoclonal antibody, then it's wise to stay as long as possible as high cell concentrations as possible. Yeah. So just for bringing that together. But for calculation of the batch time, you will need to calculate how long does it take to come up to this concentration, because this is then an exponential phase. And if then I add 2 days more on for the production, this is in addition to the batch time. Yeah. I hope this is also clear to the people in the internet. So, and now we come to an example. So a strain of Azotobacter vinelandi is cultured in a 50-meter cube stirred fermenter for alginate production. KLA is as depicted, and the solubility of oxygen is also as depicted. And what is the maximal cell concentration supported by oxygen transfer in the bioreactor? As this is so important, this is something I would like to calculate with you together, although it's so simple. But nevertheless, it's really important that you understand that calculation. So at the end, it's all about this equation. So we talk about this equation here, that X max is KLA for the concentration of the saturation concentration divided by Q0. The arts is again conversion of units. So if we just copy that to the board, and before we copy that, we remove everything else. So I need now a sheet to be able to copy. I had that on a sheet. Oops. Where is my sheet?
Solubility of oxygen changes based on whatever, like water or broth or honey. It changes based on this, right? So for every different substrate, you're gonna have to calculate the oxygen solubility. Given you're working in aerobic conditions, but like say you have a specific broth of your own making, you're gonna have to calculate the oxygen solubility for that broth if you want to get the maximum cell concentration.
So the question is, if you vary your culture conditions and so on, so your media composition is different, this has an impact on the oxygen solubility, yes. But the impact of the oxygen solubility usually is, it's not factor 50. Yeah? So what you would do is, to take that into account for a first approximation, is go for 10-20%. So if you, for example, plan to set up a company and you want to produce what you will do in industrial biotechnology, dipeptide, you remember, that's what you did. Then you don't start with, let's say, doing an experiment, what is the oxygen solubility in your bioreactor. You just say, okay, I have a 30-degree reaction, I have a tabulated value, I subtract 10%, this is fair, and with this I start my calculation. Yeah. Of course, if you then want to go if you need a real detailed calculation, then you would go on and measure it at the end. Yeah. So that's the best thing to do. This is what you did. You used, and then you put your actual medium and measure KLA transfer coefficients. Yeah. And what you measure also with this dynamic method is, you don't even measure the absolute oxygen concentration. You measure oxygen saturation. So you say you saturate your oxygen, but you don't measure the concentration. So you just calibrate your sensor to 100%. Because at the end, you don't care how much oxygen is inside. You think of transfer. Yeah?
A question is not directly, or maybe a bit correlated to the example. I was wondering, when we sparge with air, what we do 99.9% of the time, the nitrogen percentage of the air is immediately getting flushed out, and that's why we can even get an oxygen saturation of 100%. Or how is it possible with 21% concentrated oxygen?
This is the saturation in your liquid, and this comes from the oxygen, which has a partial, so Henry's law. The oxygen concentration depends on the partial pressure of your oxygen in your gas. If the partial pressure of your oxygen in your gas is, if the gas is 1 bar and the partial pressure is 0.21 bar, because it's only 21%, then of course your oxygen concentration in your liquid is lower than if your partial pressure would be 100%. So if you sparge with 100% oxygen, you will have a 5-fold higher oxygen saturation concentration. Yeah? That's clear, Henry's law. But sparging with 100% oxygen is expensive and dangerous. The oxygen itself is not dangerous, but things which are in a 100% oxygen atmosphere burn like hell. So this is dangerous. Therefore, usually you don't do that, because that costs a lot of money. And taking the risk or saving from the risk of burning also costs a lot of money.
Yeah, I mean, I understood that. What I still don't understand is when the partial pressure is 0.21, then we could assume the nitrogen also gets transferred into the liquid phase as well. But the nitrogen is, as we are guessing out, is not fixed in the liquid.
In pure nitrogen, the partial pressure of oxygen is 0. Yeah. So so you have the similar conditions of sparging, but there is no oxygen inside. So therefore, the oxygen will be you sparge in. You have gas transfer in both directions. Huh? So if you have a 0 concentration of oxygen in a gas bubble, and a saturated oxygen in your liquid phase, the oxygen will be transferred into this gas bubble with nitrogen and blown out. If you don't sparge, this process will take very long, because this only happens at the surface. Therefore, you need to sparge it inside. Of course, the nitrogen concentration in your liquid will also change, but we don't care about that.
Okay.
Because we don't measure it. Yeah?
Okay, fair
and
enough.
it will not dramatically change, because the difference is the difference for oxygen is dramatic, because it's 21 to 0%. And if we sparge in pure oxygen, it's also dramatic. It's 5-fold. But for nitrogen, it's 79% to 100%. This is not really dramatic. The problem in this dynamic method, if we already talked now about this dynamic method, is if you start switching from nitrogen to air, then of course you still have bubbles with pure nitrogen inside. So it's not that you switch and after 1 millisecond all the nitrogen bubbles are outside and all the air bubbles are inside. And depending on your KLA rates, of course, this can make a difference. So if you have very low stirrer speeds, and it takes ages for this to transfer, no problem. But at high stirrer speeds, this is of course an issue, and which we don't account for. Yeah?
Thank you.
Okay, but now we come back to our example, and now we would like to calculate it. So we start with our famous formula, X max is equal to, and this is this formula we had depicted before, divided by Q0. So our problem is that this Q0 is equal to, maybe someone can dictate and I don't always have to turn around, 12.5 millimole per gram per hour. And my solubility is, C star is approximately 8 times 10 to the minus 3 kilograms per meter cube. And my KLA is 0.17 per second. So I have everything. I have my KLA, I have my concentration, and I have my Q0. The problem is all with different units. Yeah? So that's the point. This is typical here, that it's a unit conversion point and not a calculation point. Yeah? So the point is, to what do we convert? Let's convert to seconds. grams and meter cube is fine because we have here meter cube. So seconds, or let's convert to seconds, and yeah, we can also convert to kilograms, then we don't need to convert this one. Yeah. So seconds in kilograms, then we only need to convert this term here, and this makes our life easier. So therefore, we first go from millimole to mole. Go step by step. Mole divided by millimole. And of course, then I have no space here. Mole. Of course, 10 to the 3 millimole are 1 mole. So I have kicked out my millimole, then I can convert my mole to gram. Fold. What is molar mass of oxygen? 32 grams per mole. So 32 grams per mole. Now my 32 is upside there. My mole is kicked out. I have my grams. And now I have to convert that to kilograms per kilogram per hour. And as it's gram per gram, this is of course the same as kilogram per kilogram. So therefore, if I want to convert my oxygen, then I have 32, then it's for 1,000, oxygen divided by 1,000, that I don't need to convert. Then I directly go to this kilogram, grams per gram, kilograms per kilogram. But my hour, I still need to convert. And of course, my hour has 3,600 seconds, so it's divided by 3,600. And then I am at, I get, sorry? So this is, the Q0 is per gram cells, and this above is oxygen. So it's a different gram. So you should keep them. Yeah? Don't do that. So if you wanna keep that gram in the unit, you would convert the grams of the oxygen. You would convert. Yeah. So because the value we work here is also the solubility of oxygen. So we need to come up with kilograms here. Yeah. And of course, we could also say, we can also convert that. If we want to be on the safe side and we are a bit nervous about these grams here, what you can do is convert this to grams per gram. Then you're at grams per liter, for example. Then you're on the safe side. Yeah. So you can convert that to grams per liter. And the point is, this is the same as, so 1 kilogram is 1,000 grams, 1 kilogram, but 1 meter cube is at the same time 1,000 liters. So in other words, this is the same as 8 times 10 to the minus 3 grams per liter. Yeah. So that's cool, because that makes us feel good, because also if we would have converted here kilograms to kilograms, it also would make no change, because it's 1,000. So here it's then the, let's say, more handy conversion, because this is also a unit which makes us happy. And now we can keep this gram here without any problems. Okay, calculation.
1.1
10 to the power of?
Minus 4.
Minus 4. And the unit, as we said, is grams per second. Yeah? Okay. I didn't calculate it myself, so I trust you, because I have just a long calculation. I forgot to do this separate calculation. Yeah? And now we can calculate that X max is equal to, KLA is 0.17 once divided by second, fold My saturation concentration is 8 times 10 to the minus 3 grams per liter divided by, and then I am at 1.1 times 10 to the minus 4 grams per grams volt second. So now I can kick out my grams and my liters. I would kick out the oxygen grams here to be formally correct. Yeah? Of course, lazy people then kick out these grams here, but formally this is not correct. But at the end, you should end up with the same unit, yeah? Even if you missed up the grams. So therefore, as we're lazy, we just take care about the grams here. The seconds, 1 divided by second also gets kicked out, and we end up with a concentration of grams per liter, which is a biomass concentration, which is okay. So keep the units, it's really important. Yeah? And grams per liter is more reasonable. So it was good that we converted this to grams per liter and not the other thing into kilograms. Yeah. And this is equal to 12.24 grams per liter. Oops. That looks good. So this is a reasonable concentration. So if you come up with this concentration, it's reasonable. That's also very wise to check that whether your result at the end has a reasonable magnitude. 12.4 grams per liter is a biomass concentration, which is reasonable. Yeah? Yeah, so that's the calculation here. As you see, the calculation itself is very simple, but conversion. Don't forget to do these conversions step by step. And this really helps. And units, it really helps. So some of the others might remember when they came to me during the lab course telling me, this is bizarre, I get the wrong unit. And then I watched at the calculation and I said, yes, because your formula is not correct. And that's the cool thing about units. If you get a wrong unit, either you made a calculation error, but if you're sure that it's not a calculation error, the problem is your formula. Then check whether you made an error deriving the formula. And usually the problem is that you didn't derive the formula, but you thought, this is the formula. So the error number 2 is always derive the formula. Even if the formula looks very simple, you avoid errors. It makes life easier. Okay. So the A part we have now calculated together, and your job is calculating the B part of that, and this is homework. This is on Moodle. Yeah, if Moodle works again. Okay. So, any more questions to this exercise? Any questions? No. Then we can go on. Okay. So these are easy gained half point here. Yeah. So this is very, very straightforward and quick. Now we come back to the question: what factors actually affect in our bioreactor the oxygen transfer rate? And of course, if we look at the formula here, what we can do is we can affect either KLA, we can affect KL, we can affect the surface, or we can affect the concentration difference. Now, if we dissect that, KL values are usually, in the case of very, very small bubbles, at 10 to the minus 4 meters per second, and they go up to 4 times 10 to the minus 4 meters per second if the bubbles are larger than 2 or 3 millimeters. So in other words, this KL value depends on the bubble size. Yeah, you cannot. The stirrer is always stirring like hell. So you don't hold the bubble and stir directly at the border of the bubble. So you yeah, so you cannot make this this layer thinner. So at the end, it's kind of the smaller your bubble, the smaller your KL, the better it is. And at the same time, the smaller the bubble, the higher the surface, the better it is. So it means that it's wise to produce small bubbles with an however which comes in a second. So in this, if you look in reality, the KLA values you achieve in production scale fermenters are usually in the range of 0.02 per second to 0.25 per second. What did you measure today in your experiment?
I mean, we didn't have time to do the calculations of the DNA, we just took the values of the oxygen.
Always, I like that. Usually you would have an Excel table next to you because you want to know what is, if you come to this experiment, you see this bioreactor, then you say, I want to know now what the KLA value is. Didn't you have that feeling when you've seen the bioreactor?
I was more.
Well, okay. So maybe the internet had these feelings, but they cannot express their feelings about the bioreactor over the internet. That's the problem with the internet. Yeah? Feelings get lost. Students get lost to the internet, and feelings get lost from the internet back to the reality. That's the truth about the internet. Okay, so yes, so therefore we don't have the value set, but this is the range what you can expect. And this is also if you get a result with your calculation, which is 5 per second. If you have invented such a bioreactor, you would be rich. Problem is, in such a bioreactor, even the bacteria will not survive, most likely, yeah? And the energy input in such a bioreactor will be certainly also something where your provider of electric energy will tell you, what are you actually doing there? Yeah? So that's, therefore, you always check whether your results are reasonable. That's what I always say. If you do an experiment, you should come to the experiment having already an idea what your expectations are. And if what you observe is completely different, then in 99.99% of the cases, it's not because you're close to a Nobel Prize, it's because you had a wrong calculation. That's the sad truth about that. Oh, animations to come. I think now a couple of animations come. Yeah? Stirred tank reactor, sparged. Watch the bubbles rising. Yeah? So this high-end animation, and in this case it's really important to have an animation because this really shows you, the camera wants to stay on the animation and no more on me. This shows you how sparging in a reactor like you have seen today looks like. So the stirrer will hit all bubbles somehow, affect all bubbles somehow. And it's really like it looked like. So, of course, you have heated it to a constant temperature in order that the measurement makes sense. So, therefore, you have this, this invisible heating device around. So, the other reactors which were standing next to you in the bench, they heat differently. They heat with water, so you can see directly what's happening. However, they have different stirrers. They are for high viscosity fluids, so therefore the transfer rates there are different. So we want to use them also for solids, and therefore stirring is completely different. There are lower rotational speeds, and also transfer and so on is a completely different story. But this is the bad news. You didn't see it really, but you had the feeling that it looked like. You had this small window where you could look in. Hopefully you also looked in this small window. Yeah. Now, if we go to a production scale fermenter, you see that here, first of all, the stirrer power is slower, and you see that the stirrer will not affect all bubbles at all time, at all position. So therefore, you say that there is a distortion of bubbles by the impeller, and then you have a free floating area. And that, of course, makes a difference with respect to oxygen transfer. That's clear. And the other thing is, it would be cool, our KLA, okay, as soon as I reach 2 to 3 millimeters, I will not affect my KLA anymore. However, if I get smaller and smaller and smaller, my surface area gets higher. So in principle, it would be wise to make a bubble as small as 0.1 micrometer or so, yeah? Because then the oxygen transfer will be very fast. However, the problem with my small bubbles is, if I have a very small bubble, I sparge it in to the bioreactor, then the oxygen is immediately transferred, but this bubble is still in the reactor with the nitrogen. So it's a useless bubble in a reactor. Makes no sense. So I want to optimize also the residence time of this bubble in the reactor, that as it starts to transfer oxygen from the downside, and when it leaves, it's ready. Because it occupies also volume in the reactor. And if I have 90% of my bubbles have already finished with their transfer and stay in the reactor, this is of no use. So therefore, it makes no sense to go to close to zero. It's an optimization problem rather. Yeah? Now, the other problem is that if I have small bubbles, is that they remain lodged in the medium. So you have the tendency to go up, and if you're a large bubble, you go up quickly. If you're a small bubble, you take your time. Yeah? So, and if you're too small, the bubble doesn't find the way out anymore. Yeah? This is also what you want to have, especially if your medium is more viscous. And of course, the other problem is form. So this is what I always would like to do. And now the first student came and said that the experiments of Frank are more beautiful than my experiments. One student said that, okay. But I said directly to Val, we have to change that. Yeah? We have to work on that. Yeah? So what we always plan to do is we want to include in the chemostat reactor form control. Which is really cool, because then we have electrodes and we have Arduinos doing everything, and we have an additional pump which is controlled by the Arduino, which pumps in antiform. And as we are too stupid to check this control with the Arduino, this has been programmed by Frank, but we want to implement that. Yeah? So, because it's cool. Yeah? So then we have an additional level of engineering. But Weil always said, hey, wait, we have already 50 tubes hanging around. The students are already confused. But now I said they came and said Frank's experiments are more beautiful. We put that to this reactor. This is the last time that I hear that. Yeah, we need more things hanging around at our reactors. Okay, so now this is the gas holdup, and this is what I said, that these small bubbles take a long time to get out of the reactor, and large bubbles quickly go out. And this all goes together in reactor design. So that means it's good to be small enough, but you should not get smaller than you absolutely need. Yeah? So this is what you adjust with also your stirrer. Yeah? It makes no sense to stir like hell if you don't need it. This is a waste of energy also.
Only valid for air, is it only valid for air or also for pure oxygen?
That's the same. At the end, it's the same, because the pure okay. What you're referring to is that pure oxygen, of course. Then the bubble is empty. Yeah, that's yeah. You're right. However, you also transfer in the bubble carbon dioxide. So usually carbon dioxide is produced, which goes in the gas bubble. So your gas bubbles will not disappear.
Okay, thanks.
Yeah. Okay. Now, how can we influence KLA and our bubble size? And we talked about that. This is what you did today. In principle, sparge and bubble formation is something what you can change. However, in our stir tank reactors, what affects bubble size is the stirrer. So if you have, of course, an airlift reactor, that's the only thing you can do. But unfortunately, the bubbles don't stay as they do at the beginning. They coalesce and so on, and you have this very complex patterns. You will see that when we look at reactor designs. Now, a short excursion on mixing. So this is how a stirred tank reactor in reality looks like. And this is also how your reactor you worked with today looked like. You have a motor on that, and you have an impeller. Usually these impellers look like that. You have the sparger below the impeller, and you have baffles. And then, of course, you can you have several design factors which goes into that. So this is the geometry of the reactor. And then you can, depending on what impeller you use, generate different flow patterns. So this is the typical flow pattern you use with a radial flow impeller, where the baffles are like this. So you press the liquid to the sides, the baffles disturb, and then you have a rotation. You rarely use an impeller like this, which create this axial flow pattern in a bioprocess. So if possible, you use this one, and you will see in a second why. Because this is not the only impeller design, so you can do also different ones, and these are also used, but it depends on what you want to do, and it depends on how viscous your liquid is. And you see that, for example, these dispersers, they rotate with very high speeds, can generate then therefore a very high turbidity, but it doesn't work at, they don't really transport the liquid. That's one problem. And the second problem is that with higher viscosities, it doesn't work at all, because they will just run, they will create their air stuff, and they will don't even hit the liquid anymore. So this means the impeller use depends on what you want to do. So if you have, so these gates and rakes has a very low turbulence generation, but they have a very high pumping of flow capacity, and therefore they're good if you have a high viscosity. There you need to have this capacity to do. However, of course, mass transfer with oxygen is limited, because you cannot generate this turbulence and so on. But this is also impossible in highly viscous fluids. So usually these Russian turbines are the things you use because they have a substantially high turbulence generation, but still have a good pumping flow capacity. So they're the best compromise usually in an aqueous medium, which is usually of a low viscosity. So therefore these impellers are optimal. That's the reason why these are usually used. Now, this is something I just want to quickly come over. You'd remember we have discussed 20 minutes about, I have forgotten what we have discussed about, what we have discussed 20 minutes about something. Sorry? Bachelor thesis. How could I forget that? Okay. So, because I would like to end this mass transfer, that you come to the last homework and you have done it, and then we can discuss next time on the homework. So kind of, you have two things. You blow in, you sparge in your air, and you rotate your impeller. And intuitively, it's clear, if you sparge in air like hell, and your impeller then more or less operates in an air bubble, then something is going wrong. So this rotational speed and the airflow has to be somehow in a certain ratio. And this is exactly what is said here, that if you increase your gassing rate and keep your rotational speed, if you increase the rotational speed and keep your gassing rate constant, that you can then come up to this complete dispersion. And this is what you want. Complete dispersion means that you have a turbulent characteristics, but you have a dispersion which goes in all directions. And long story short, you can calculate that. This is, of course, something which is empirical. And then you have these gas flow numbers, Frode numbers, and then for a Russian turbine, you can come up with these numbers of the floating loading transition and complete gas dispersion, and then you can, of course, plot that also. Yeah? Again, usually you know your reactor. So you know when this behavior occurs, and you don't want to have, of course, an impeller flooding, that you have a slowly rotating impeller, and the impeller never touches the liquid because you sparge way too much air through this impeller. But you can approach that if you know your reactor geometry to calculate when the problem might occur. Oops. Other things which affect, yes?
This slide with the little man, it has these formulas that they're not relevant for us.
I don't want to say that they're not relevant for us. But I would say that if there is the little man, I rushed over these Russian turbine formulas. The likelihood with a little man and rushing over to see that in the exam comes very close to zero. Never say it's zero, but very close to zero. In case of doubt, of course, also these formulas are in your formulary. But they are. But they will not come in the exam. Yeah. Okay. But of course, the internet is warmly invited. If you feel that this should appear in the exam, you're welcome to say, please. And this is anonymous. We just hear the voices.
We know your voices.
We know, okay, we know your voices.
Know where you live.
And we know where you live. Okay, so just a hint to the internet.
Please don't, isn't please, right?
Sorry?
Please don't, isn't please, right?
Please don't. So the internet also goes with you. Okay. The internet is with you. May the internet be with you. Okay. Bubble coalescence is what our nice zero works, and now bubble coalescence is of course a process which counteracts what we try to achieve. We made small bubbles and then they meet again and then they will be big again. So this is of course we want to counteract. But of course it does not just depend on our stirrer, it also depends on the liquid. So it depends on are there surfactants and so on in the liquid and so on. So the cool thing is that pure water is coalescing, and usually as soon as salts and ions are inside, coalescence decreases. So usually the liquids we work, our media, are less coalescing than water is. So that makes us happy. Yeah? Viscosity, of course, is an issue. So you will directly have an influence on bubble size, gas holdup, and KLA. And if you go to high viscosity fluids, the KLA values you can achieve are dramatically lower. So an aerobic process, and you want to obtain exponential growth, not limited with oxygen in a highly viscous fluid, hard to obtain. Remember, you can still get growth, but this will be then oxygen limited and will be slow. That's the problem if you go with highly viscous fluids. Temperature is, of course, an issue. The problem is the solubility of oxygen also decreases with increasing temperature. The diffusion, of course, is faster, but solubility at the same time decreases. So therefore, the net effect depends on the temperature range where you are. And you see here that the temperature range we are talking about, usually in a temperature range 10 to 40 degrees. If we increase the temperature in this range, we decrease the oxygen the oxygen solubility, but still overall, we rather increase the KLA value. But it's not like increasing the temperature will substantially increase the rate. This is not the case. Cis-speed and gas flow rate, you have done the experiment. I don't have to talk about that. Unfortunately, in real-world experiments, and this is what we will do next year, we will have then our antiform control. Antiform agents negatively affect KLA values. So you want to go down with your surface tension. This is what the intention is of an antiform agent, but also the KLA agents can the KLA value can drop. So, and sometimes, some cases you have even 5 to 10-fold decrease in KLA. And of course, the problem is that antiform at the beginning of your culture, form is not an issue. Form usually becomes an issue at higher cell densities. And the problem is this is exactly when you want your higher KLA values. And then you need to add tons of antiform. This problem is that if you have determined your KLA value with your dynamic method, in a real, and you say, okay, 20% because the medium is a bit different with solubility and so on, and then you estimate your what your cell density you can obtain. And if in your case you need a lot of antiform because the microorganisms produce polymeric substrates stabilizing form, then it could be that you kick down your KLA value substantially. So at the end, you are way away from what you had at the beginning.
Why does it go down and then move up the KLA when you add the antiform?
It's an experimental value.
Yeah.
So
okay.
I didn't do this experiment.
Yeah, okay, sorry. But this is not supposed to do that. It's supposed to just go up. Do you say so?
Yeah, is it going down and up? This is the question. You could also interpret that as after concentration of 0.1, it remains more or less constant. This is how I would interpret that. Because it's you know how to measure KLA values. This is not so simple, and it's of course also error prone, because this is then in a medium, in a culture, or with these antiform agents. So there are no error bars on this, so you cannot say how significant this is. So this is a rather qualitative experiment, and of course 5 to 10-fold is an extreme case. However, you need to keep that in mind if you design a real process. This is your job then later on as a bioprocess engineer, that if you see completely unexpected results, no growth, it could be that you have to use a lot of antiform, and therefore your KLA value goes down, and this affects your growth. So it's not the antiform directly affecting your growth, it's the antiform affecting the oxygen transfer and affecting then your growth. Of course, that makes a difference. Yeah. Okay. Gas pressure, oxygen partial pressure, we can of course go up. So we can use 100% oxygen, or we can increase the pressure. We can use a reactor which is under 1.5 bar. In both cases, this increases the costs quite substantially, and therefore you should think of whether this is good or not. Now, how to influence KLA and bubble size, presence of cells and macromolecules, this is what we have in our culture, and unfortunately this also affects, without any antiform, also itself the KLA value. And if you have these fancy cells with a structure like streptomyces, this heavily affects KLA. This is less substantial if you use cells like E. coli or so, which are not forming these micelle-like structures. Yeah. However, also this is something which needs to be kept in mind. So this I want to switch. Yeah, because now we come to the way to measure oxygen transfer, and we can do two things. You have measured oxygen transfer rates using the dynamic method. So you have sparged in nitrogen and then measured the oxygen transfer, because you measure the kinetics, and you measured the kinetics oxygen gets in, and with this you have then calculated the KLA value. And of course you can deduce that. Today we have no time to deduce it, but we have enough time that you can start with the homework.
Wait, one or two homework today?
So you remember the homework you have is putting two values in one formula. So therefore you ask that, may you give us another homework where I can also put two other values in one formula. And that's the reason why we do that you have these two homeworks that we can discuss next week and finalize the section. Yeah? But what you do, the other homework, is calculating KLA with the dynamic method. So that's what you already have done anyhow. So therefore it will be simple. But I just want to end this up because this is also in line with what you did. So back to what I said. So what you did is no cells, and you put out the oxygen, and you measured how fast it goes back. But of course, what you could also do is, you remember we have this equation that we say the oxygen consumption must be equal to the oxygen what is being transferred. So if I know this, and this means that if I balance what oxygen, if I put in 21% oxygen at the beginning with a gas flow rate of 5 liters per minute, and I end up with just 5%, I can simply calculate, doing a mass balance, what has been consumed in between. And of course, the oxygen what has been consumed in between has to be the oxygen what has to be transferred. Obvious. And of course, this is then equal to the oxygen transfer rate. Oxygen flux and oxygen transfer rate, if I divide that then with the volume. Yeah? So this is a method which is of course always used because you measure usually, especially as production scale bioreactors, this constantly. And then you can apply these formulas here, and you can, using this mass balance at a steady state, you then can calculate the KLA value obtained by 28 if you have this oxygen transfer, if you have the concentration, and then you can calculate it. To do that, you need to know the oxygen concentration because you have a mass balance in this case. You need to know precisely your gas flows, usually not volumetric flows. You measure them then via mass flow instruments, which we also use in our bioreactors. They have mass flow measurements. Because the difference in this term here, so this is the difference what comes in and what comes out. So the concentration in versus out can be small. And especially if I'm in lab scale, if I have a low amount of biomass inside, the difference is small. In production scale fermenters, things are usually different. So therefore, it's more easy to measure this in production scale fermenters using this method. Yeah. So for production scale, cool method. For lab scale, usually not so cool, but there is a question.
So you said, oxygen in equals oxygen out, so you're gonna have to keep a check on how much to put in.
No. Oxygen in equals oxygen out.
Sorry. Oxygen in equals oxygen consumed. And you're gonna...
Oxygen in minus oxygen out is equal to oxygen consumed. Mass balance.
And to keep a high rate of consumption, you're gonna have to... Would you keep the oxygen in based on the bacteria, or would you...
At present, I'm just interested in measuring my KLA. This is my intention. Yeah. So I want to know what the KLA is in my bioreactor. And I can measure the actual KLA based on the mass balance. That's what I want to say. So the intention here is measuring KLA. Intention is not mass balance or whatsoever, having an idea about the KLA of my system. Yeah. And of course, as soon as it becomes limiting, then the oxygen transfer will come to a place where you cannot, the difference will get constant. And then I know, this is the maximum. So you can just measure that, plot the KLA, go up with the biomass concentration, and at some point the KLA will not increase anymore. Yeah? At low concentrations, the KLA will be small, but it will go up, and then it will come to a plateau. And that is the maximal KLA I can achieve in this system then. Yeah? Okay. So, and of course, also I need to have a homogeneous condition in my fluid phase, which means that I need high stirrer powers. And this is then again a bit difficult in industrial scale fermenters. Yeah? Okay. This is how you can measure that, but this calculation we won't do today, because what you have done is the dynamic method, and what I like to ask you is to do the homework calculation. There's no more, it doesn't appear. Yeah, this example 13 calculation, because this is what you have done also, and we will discuss that next week, and we will also discuss again some more points to consider in this case. This homework, what I might do is that you also have the chance to do that 2 days after the lecture. But I recommend to try it before the lecture. Yeah? And there is a final question.
It's more about the homework in general. Is it possible maybe to put, instead of 60 minutes after the first try, 30 minutes?
Yeah.
30 minutes after the first try?
Yeah.
Yeah.
That would be nice.
Okay. This should be possible.
Yeah,
The point is why I put this 30 minutes or 60 minutes. The problem with the homework is, again, usually not the people sitting here in the lecture. The problem with the homework is the people you never see. And if you have no time limit in between, they just do it as soon as they have their 60%, and then they're done. And of course, that's useless. The 60 minutes allow you to think of what did I make wrong. You do that, and you say 60 minutes is too long, it's 30 minutes, and then it's fine. But you see, for you, these 60 minutes are not there. Yeah? So I put that to 30 minutes. Yeah. I understand that 60 minutes is long. What can happen during 60 minutes? 5 friends call. Why don't you want to come to our bar? We do a systematic study on cannabis. Do you want to participate? Other professors may offer these studies. Again, this is... And I want to end this lecture in telling again, cannabis consumption is illegal. And then, as you know this, I wish you nevertheless a nice weekend, because here it's not too far away from the Netherlands. So I think it's not too hard. So wish you a nice weekend. Enjoy the remaining simulations, and looking forward to seeing you again.